Yesterday we have talked about the introduction of the basic fundamental principle of quantum chemistry. It was derived by Erwin Schrödinger, and thus that equation is known as Schrödinger's wave equation. Now we are going to discuss operators in quantum mechanics. So this concept is very much new to you, because you may not have gone through the quantum mechanics, and you might have studied some principles or some laws like uncertainty principle or Heisenberg's principle, Max Planck quantum equation, and all these things you might have gone through, but actually it all derived from the quantum mechanical studies conducted by them. So now we are just going to discuss about operators. Operator means, in case of classical physics, that means the larger objects. When we talk about the observable things is its position of the planet, for example, and the momentum of the planet, and also the velocity of the planet. All these are observables. And here in quantum mechanics, so we have taken certain things like operators that is very much associated with the observables. If we, for example, like if you talk about the position, there is an operator related to the position. And if you talk about the momentum, so there is an operator related to the associated with the momentum. So that is what operator means in quantum chemistry or quantum mechanics. So here an operator is an instruction to carry out a mathematical operation upon a function. So it is purely a mathematical operation, and it is done on a function. So a mathematical operation is just like a surgery doing on a man or a person. It is just like a mathematical operation upon a function. A function is required, which is called an operand. Function is called an operand. So an operator is an instruction. So we are giving instruction to carry out a mathematical operation upon a function, and it is called operand. The function is called operand, and it is a procedure that transforms a given function into another function. So once we are giving a mathematical instruction for a operator to act on a function, it will be converted into, the function will be converted into another function. So there is some mathematical operation is taking place in order to convert the function to another function. So that is the role of operator. The operator is usually denoted by a capital letter with a caret. Caret means circumflex, they call, or it is just like a hat. We can say its symbol is just like a open triangle. The arrow part is at the upward direction, and let a hat, circumflex or caret, or we can call it as a hat. This we can call hat, topi, symbolizes an arbitrary operator. We just indicate an operator. So normally an operator is represented like this. Should be a capital letter, and then above it there should be a hat. So we call it as a hat. To indicate a hat, a operator acting on a function fx, we write a operator acting on fx. Fx is a function. The operation gives a new function. So then only if we get a new function, then only there are some mathematical operation has taken place. If a operator transforms the function fx into another function gx, we write the relationship as a operator acting on function fx equal to, we get gx. So this fx is converted into gx, or transform a operator transform fx into gx. So in this equation, log ln equal to ln a equal to b. So log is an operator acting on the function a is converted into b, or the operator ln, log, natural logarithm of a, or a log operator converted a into the function a into b. In the log operator takes the natural logarithm of a and then transforms it into b. So this is what an operator means. And now we consider another equation, x fx equal to y. So x is an operator acting on the function fx that will be converted into y. So x is an operator, multiplication of x of the function to its right transforms it into a new function y. So a mathematical operation has taken place here. Similarly, d by dx is an operator because differential of it is acting on one function, then only that will be converted into another one. D by dx operator operating upon the function yx and transforming it into its first derivative dy by dx. Okay, so likewise in square root of 2, square root symbol is a mathematical operator. So it is acting on the function 2, and then 2 will become the square root of 2, we get the square root of 2. So 2 is converted into another function. Likewise, square integral 5 multiplied by 5. 5 is a operator acting on another function 5. Then we get 25 as a result. Then that 5 can be considered as an operator. Del by del y is a partial derivative, is also an operator. Log is an operator, etc. are also operators. So wherever we give a mathematical instruction to carry out a mathematical operation, all those are normally operators. So this should be related to the physically observables. Even though an operator without an operand following it has no physical significance, an operator cannot stand alone. Likewise, just take here the square root. If you just put square root, it doesn't have any meaning. There should be a function following the operator. Then only it has any meaning. Otherwise, it doesn't have any meaning. Okay, now we have to see operator algebra. Sum and differences of two operators. How can we perform operator algebra just like the algebra in mathematics? The sum of two operators, A operator and B operator, is defined by A operator plus B operator acting on the function fx. So this we can write it as A operator acting on fx and then B operator acting on fx. And for instance, we just give the A operator as d by dx, B operator as x, and fx function fx equal to x square. And then we perform the summation and the sum and differences of these operators. A operator plus B operator fx equal to A fx plus B operator fx. Then we just substitute the values of A operator d by dx. We had given here fx is x square, we had given x square, plus B means x into fx is x square. So we get 2x plus x cube. So similarly, we can find the differences of these two operators, operator A and operator B. Likewise, we can write like this, and then we can find the value. We just substitute A operator value, fx value, B operator value, fx value. Okay, so it has not done here anyway. So you can just try to perform it, then you will get the value. Next, what are the product of two operators? Product of two operators is different than the normal multiplication. In normal multiplication, we can easily interchange the functions or just like operator, but in this case, the operators, in certain cases, operators can be interchanged or cannot be interchanged. So here two cases arises. One is a commuting and non-commuting operators. Two operators maybe. So multiplication or the product, we have to take at least two operators, and two operators may be commuting. Commute means interchange each other. May be commuting, and non-commuting operator may not be interchanged each other. Okay. So we have to discuss how the operators are commuting and how the operators are not are non-commuting operators. The product of two operators can be written as, for example, we take A operator, B operator acting on fx. So this is the product of two operators. Two operators are written together, and then fx. Then we written we have written a function, and here A operator acting on B operator fx, and similarly we can write it as B operator A operator acting on fx. Both should be equal, but in case of operator algebra this case is different. The notation A operator acting on B operator acting fx means that we first apply the operator B to the function fx, and then whatever we get, A operator is acting on the resulted function, and to get a new function and then apply the operator A to this new function. Suppose for two operators A operator and B operator, it is found that A operator B operator fx equal to B operator A operator fx. That means A operator acting on the function of B operator acting on fx. And this should be equally true if we write it like this: B operator acting on the function of A operator acting fx. So then we may say that the two operators A and B are commutable. That means interchangeable. If we put A here and if we put B here, and if we put B here and if we put A here, both are same. This equation 2 means both are same. That means A and B operators can be interchanged. That is commutable. So we call A operator and B operator, in this case, if it satisfies this equation, are commuting operators. And now we take equation 1. It can be written as, you take the RHS to the left hand side, and then A operator B operator fx minus B operator A operator fx equal to 0. And next step, we take the function outside, A operator B operator minus B operator A operator fx equal to, here we just put a null operator. 0 hat is what is called a null operator acting on the function fx. So apparently this means 0 only. So we just put this function as it is like this. And this is what is called a 0 operator or a null operator. Okay. And then here no special property for fx has been used to arrive equation 3. So in this equation we did not give any particular property to arrive this fx. Okay. And then we have to suppress this equation as A operator B operator minus B operator A operator fx is removed. Okay. And then 0 hat, 0 operator doesn't have any meaning. Okay. So we just put 0. Okay. So here the point is given. It is the usual practice to omit the circumflex hat over operators like the null operator and the unit operator. If it is one operator, the result is same, which designates simply multiplication by a constant. So now the LHS of equation 4, so we have to take this equation 4, is called the commutator of the operator A and B. So now A and B, B and A. So when we take A and B, and when we take this term to the right hand side, A and B equal to B and A. Okay, A operator B operator equal to B operator A operator. That means these two are interchangeable. That means these two operators are commutable, commuting operators, and is usually written as A operator B operator in square bracket. A operator comma B operator in square bracket if these two operators are commuting with each other. And then equation 4 we can write it as A operator comma B operator in square bracket equal to 0. This equation satisfies only when these two operators are commuting to each other or these two operators are interchangeable. In other words, the two operators A operator and B operator are said to commute each other if their commutator is the zero operator. Commutator means A operator and B operator. So these two are the commutator operators. That means these two can be interchanged. So, and if this is equal to 0, interchangeable is possible. If this is equal to 0, then we can call it as a commuting operator. And suppose when we take another way of the equation 1, equation 1 is this one. Just look at the equation 1, and then equation 6 we have written as a hat b hat over fx not equal to b hat a hat over fx. Here we have written equal to equal, and in this case we have written unequal. These two are not equal. And then this means that a operator acting on the function of b hat on fx not equal to b operator acting on a hat fx. Then we say that the two operators a and b do not commute, and that a hat and b hat are non-commuting operators. So this effectively means that a hat comma b hat in square bracket not equal to 0. Okay, understand? It is obvious from equation 6 on applying the same argument that where we used to arrive equation 5, two non-commuting operators a hat and b hat, a hat b hat minus b hat a hat not equal to 0. In other words, the two operators a hat and b hat are said not to commute each other if their commutator is not the zero operator. Okay, this is just the reverse of the previous one. Now we just have to check the product of two operators by substituting the certain values for it. The products of two operators a and b is defined as a operator a hat b hat fx equal to a hat acting on the function b operator on fx. So first we have to do this one. B operator we have already mentioned in the previous sum and differences of operator, b as fx and fx as x square, and a operator is d by dx. So here a operator d by dx we have written, b operator's value is x and fx value is x square. First we have to do this calculation operation, and then equal to d by dx equal to x cube. So this is 3x square. So we arrive this value when we perform a operator is acting on the function of b acting on fx, b operator acting on fx. Okay, and now we will do the next case. We take this b operator outside and operator inside. Okay, so b operator acting on a hat over fx. So this is equal to b, the value of b is x, and then a is d by dx and fx is x square. Okay, so here first we do this operation. So we just put this value, this operator exactly as it is, and then this value is 2x. This operation will give the value 2x, then we get 2x square. So this means that here we get 3x square and here we get 2x square. That means the operators a and b given here are not commuting to each other, non-commuting operators. Thus here a hat b hat not equal to b hat a hat. In such a case we may say that the operator a hat and b hat do not commute, or that they are non-commuting operators, because we are getting two different results when we perform the operation. Some pairs of operators commute while some other pairs do not. So that is a major difference when we see the product of operators. So here there is a direct relationship between the commutability or non-commutability of two operators and the simultaneous measurability of precise values of the two physical quantities for which the operator stands for. So this point means that in case of we are coming to the uncertainty principle, this point means that if we in uncertainty principle it states that we cannot measure precisely the position and momentum of a moving subatomic particle, right? So this is momentum. We cannot find precisely the momentum and position of a moving subatomic particle. Okay, so that's what uncertainty principle says. So we can either measure any one of the either position or momentum as far as, for example, like an electron is considered. Okay, so that's what uncertainty principle. That means the operators are not commutable, are normally considered in Heisenberg's uncertainty principle. So we will discuss it. If two operators commute interchangeable, then the simultaneous measurement of the precise values of both the physical quantities for which the two operators stands for is possible. ഇവിടെ പറയുന്ന മലയാളത്തിൽ ഞാൻ പറയാണ്, ഇവിടെ പറയുന്ന കേസ് ഇത്രയേ ഉള്ളൂ. നമ്മൾ നേരത്തെ പറഞ്ഞ ഓപ്പറേറ്റേഴ്സ് രണ്ടെണ്ണം, എ ആൻഡ് ബി എന്ന് പറയുന്ന രണ്ട് ഓപ്പറേറ്റേഴ്സ്, അത് കമ്പ്യൂട്ട് ചെയ്യാൻ പറ്റുന്നുണ്ടെങ്കിൽ നമുക്ക് സൈമൾട്ടേനിയസ് ആയിട്ട് രണ്ട് ഫിസിക്കൽ ക്വാണ്ടിറ്റീസിനെ മെഷർ ചെയ്യാൻ പറ്റും. പൊസിഷനും മൊമെൻറ്റും, ഫോർ എക്സാമ്പിൾ നമ്മൾ അൺസർട്ടനിറ്റി പ്രിൻസിപ്പിൾ പറയുകയാണെങ്കിൽ പൊസിഷനും മൊമെൻറ്റും ഓഫ് എ മൂവിങ് സബാറ്റോമിക് പാർട്ടിക്കിൾ പ്രിസൈസായിട്ട് കറക്റ്റായിട്ട് നമുക്ക് ഒരേ സമയത്ത് സൈമൾട്ടേനിയസ് ആയിട്ട് മെഷർ ചെയ്യാൻ പറ്റും എന്നാണ് ഓപ്പറേറ്റേഴ്സ് കമ്മ്യൂട്ടിംഗ് ഓപ്പറേറ്റേഴ്സ് ആണെങ്കിൽ. സമയം നോൺ കമ്മ്യൂട്ടിംഗ് ഓപ്പറേറ്റേഴ്സ് ആണെങ്കിൽ, ഇഫ് ടു ഓപ്പറേറ്റേഴ്സ് ഡു നോട്ട് കമ്മ്യൂട്ട്, then the simultaneous measurement of the precise value of both the physical quantities for which the two operators stands for is not possible. ഇത് രണ്ടും നോൺ കമ്മ്യൂട്ടിംഗ് ആയിട്ടുള്ള ഓപ്പറേറ്റേഴ്സ് ആണെങ്കിൽ we cannot simultaneously measure the precise values of both position and momentum of moving electron. Okay, അപ്പോൾ അതാണ് ഇവിടെ അതിൻ്റെ സിഗ്നിഫിക്കൻസ് വരുന്നത്. ഹിയർ statement 2 is reflected in the famous Heisenberg uncertainty principle. The mathematical basis of this principle is that the operators associated with the momentum and position of a moving subatomic particle do not commute with each other. Yes. And then hence the two quantities cannot be measured simultaneously to any desired degree of precision. This is what the basis of Heisenberg's uncertainty principle. We cannot measure precisely the position momentum of a subatomic particle. Next, last one in the operator algebra is the square of an operator. The square of an operator is defined by, we can write it as a hat square fx equal to, a hat square means a hat into a hat. So here a hat into a hat fx, and then a hat value is substituted as d by dx, and then fx value is x square. So here we just substitute here d by dx of x square, d by dx of 2x equal to 2. Okay, hence in this case d by dx all square equal to d square by dx square, both are same. Okay, so that's all about an operator algebra, and you have to read it very carefully. നിങ്ങളിത് നല്ലപോലെ തന്നെ വളരെ കെയർഫുള്ളായിട്ട് തന്നെ മുന്നോട്ട് പോകണം, അല്ലെങ്കിൽ നമുക്ക് പെട്ടെന്ന് മനസ്സിലാക്കത്തിരി ബുദ്ധിമുട്ട് ഫീൽ ചെയ്യും. നേരിട്ടുള്ള ക്ലാസ് അല്ല, ഓൺലൈൻ ക്ലാസ്സാണ്, അതുകൊണ്ട് തന്നെ ഷുഡ് ബി വെരി കെയർഫുൾ. ഓക്കെ.